Thảo Phương. Giáo sư Thảo Phương tốt nghiệp Đại học Sư phạm năm 2009. Thì năm 2013 giáo sư Thảo Phương lấy bằng tiến sĩ tại Đại học Marie Curie. Sau đó giáo sư Thảo Phương có làm việc ở Đại học Sư phạm từ 2014 đến 2017. Từ 2017 đến 2018 Thảo Phương làm postdoc ở U of South Carolina, và giáo sư Thảo Phương đã làm giáo sư ở Đại học Auburn từ 2018 tới nay. Và bữa nay giáo sư Thảo Phương sẽ nói về domain decomposition-based exponential time difference methods for stiff evolution problems. Mời Thảo Phương.
Okay, đầu tiên là em xin cảm ơn ban tổ chức đã tạo điều kiện để cho mình được trình bày báo cáo tại cái hội nghị CAAM lần thứ 2 này, và xin cảm ơn mọi người đã tham dự buổi báo cáo. Trước khi báo cáo thì cũng xin nói trước là background của mình thì nó tương đối khác với lại hầu hết audience ở đây. Để cho tiện trình bày thì xin được nói bằng tiếng Anh từ bây giờ. Hey, so my research interests are numerical PDs and computational math, so it's quite different from the previous talk. So I'm more interested in the applications, like my purpose is to find numerical solutions and sort of trying to derive efficient algorithms with real application in mind. So it's quite, so it's just some different point of view. And for this talk, the purpose is not to go into details, but instead I try to give sort of a picture of what I'm doing. And also like, I would like to give some ideas. So if the students or anyone are interested, just let me know for further details. Okay, so previous talk is about PDs, SD and SPDs. My talk is most likely about ODs. So basically, I'm going to talk about efficient time steppings for stiff evolution problems, so stiff differential equations. So this is a joint work with Lily Zhu, Zhu Wang at University of South Carolina, and the two postdocs there are Sally and Xucheng Meng. Okay. So here's the outline of my talk. So basically there are 3 parts. So I spent a few slides to introduce to the so-called exponential time differencing methods. So it's a kind of time integration method for ODs. And then in the second part, I will spend most of the time here where I developed the so-called localized ETD method for the semilinear parabolic equations. And then later I'll briefly present the algorithm for shallow water equations, and finally some conclusion. So an overview of time integrations for ODs. So if you're given a initial value problems like this one. So dy dt equals some function g on the right-hand side. And here I'm interested in finite interval. So from 0 to capital T, and some initial conditions at t equals 0 or t equal to 0. And so for numerical, so I'm interested in numerical approximations. So the first step is to discretize our time interval, right? From 0 to t, so I will have the grid points, so ti or tm here with the distance delta t. So I'm going to find the approximations ym at each tm. So I list here 2 basic methods, very basic. It is explicit Euler and implicit Euler. So basically, you just integrate these equations from Tm to Tm plus 1, and then you approximate the integrals by just constant. So G here is you treat like piecewise constant functions. So depending on which endpoints you evaluate G, you can have explicit Euler. So here you evaluate G at Tm, Ym, and for implicit Euler, you evaluate at the next time level, which is Tm plus 1. So this one is explicit since you can compute the approximations y n plus 1 immediately, given the solution at Tm, okay? While for implicit Euler, you have to do some solver in order to compute y n plus 1 because it appears on both sides of your equation. So for time stepping method, stability is a crucial issue. So here I listed a very basic stabilities criterion, which is the linear stability. So for the linear stability, we look at this linear equations. So this is our test equation. So this is just lambda multiplied by your solution y. And here lambda is considered to be, so here for simplicity, I consider only real. And it has to be negative here because for lambda greater than 0, the problem itself is not stable, in the sense that if you have small perturbation in the initial conditions, it might lead to large changes in the solution. So for these test equations, you have the exact solution, which is an exponentially decaying functions given by this formula. So it's just y0 e lambda t. So it is important that your numerical solutions also have this behavior that is a decreasing function. So for explicit Euler, in order to maintain that properties, you will need to enforce these conditions. So your delta t, we call it time step size, must satisfy this inequality. So it depends on the value of lambda. In particular, the larger lambda in magnitude, the smaller delta t has to be. So we call it conditionally stable. And for implicit Euler, it is unconditionally stable in the sense that delta t, the time step size, is independent of lambda. You can choose delta t as large as you want. So that is stability analysis. Just some brief recall for students, since I was told that there are many students attending the conference. So now I'm going to switch to something else, as is the exponential integrators, another way to do time stepping. So in the previous slide, I just listed some very basic methods to illustrate the implicit, explicit method and their stability. Okay, so now I switch to this type of OD. So we have a system of OD. Here, my unknown is a vector u in Rn. So for each t, my function is a vector function. And it satisfies this system. So here on the right-hand side, it has the following form. So the right-hand side is a sum of a linear term and a nonlinear term. So this equation is particularly resulted from the spatial discretization of semilinear parabolic equations. I'll go to this semilinear parabolic equation in the next slide. So for now, just stick to this form. And I would like to do time stepping for this system.
Excuse me, can I have a quick question?
Yeah, sure.
Yeah, I'm just curious about the operator L. So is it a linear operator depends on T?
No, L here is just the spatial discretization of an elliptic operator. So it's like Laplace.
Okay, cool.
Second order elliptic operator. It's not depending on T, it's depending on U. I mean, not explicitly on T.
Okay, yeah, so it's linear in U, right?
Exactly.
Yeah.
I wrote L for linear.
Yeah.
So it's a linear term and non-linear term.
Cool, yeah, thank you.
Okay.
May I have a question too, please?
Yeah, sure.
What about the property for the function u in this case? Is that absolutely continuous, or what kind of property that you put on the function u here?
So it just have the sort of standard regularity so that you have a unique solution to this system. So it's L2 in a weak sense, so it's L2 0t.
I see. So it might be, we can replace it by a measurable function. Do you think so?
I'm not really so Here again, so for my work, I most likely assume that the solution is there and it possesses some nice properties, and I more likely want to find approximate to the solutions. So it must have some nice properties so that I can have, sometimes I require more regularity than it actually is. However, for the numerical simulations, usually our theory requires higher regularity, but the results can also, the algorithm can also work under sort of weaker regularity.
Yeah, thank you so much for your answer.
Okay, I hope I answered it. However, here, what I want to say in this context is that for this equation, I'm interested in the case where we have a stiff system. So what does it mean by a stiff system? So let's go back to the previous slide. So in this slide, just this case of when lambda is very small, that means strictly very small compared to -1, for instance, then your explicit Euler method become inefficient because you have to use a very small time step in order to have stability, while implicit schemes work much better. So that is one example of the stiff equations. And here when you have a system of ODEs, I say it stiff in the sense that it can be both actually. So the stiffness can come from the linear terms, or it can come from the nonlinear term. Here, I restricted myself to the case where the stiffness comes from the linear term only. So for the linear term, the stiffness means that the eigenvalues of your L, in this case, just a matrix actually, L is just n by n matrix, is large or have or their eigenvalues differ greatly in magnitude. So in that case, we're gonna have the trouble with explicit methods in the sense that it requires very tiny time step size. And this requirement come from stability reasons, not come from accuracy reason. So if you impose larger than some threshold, you just blow up. So you have unstable situations. So that means stiffness here. However, if one use implicit method, it can be costly because of the nonlinear term. So here you have the nonlinear term f on the right-hand side. So if you do implicit, then the right-hand side will have un plus 1, for instance. Then you have to do some nonlinear solver. So depending on the problems, the nonlinear solver might be very costly. Okay, it really depends on the problems. And so that motivates the so-called exponential integrator. So it's another kind of time stepping method for OD. So the idea is as follows. So so we consider just the homogeneous case, homogeneous linear system. So you have du dt equal to Lu. Then you have the exact solutions as a matrix exponential solutions. So here you have e to lt. So if L is an n by n, then e to lt is also an n by n matrix, and it is computed by this infinite series. Okay, and its derivatives are as follow, and its inverse are as follow. So e to lt here is a square matrix, and so that's your solution to the homogeneous equations. And as you know from the elementary differential equations course, when you have the non-homogeneous differential equations, you're gonna have the complementary solutions, which is this one, and you compute the particular solutions. And here I'm gonna use a variation of constants or variation of parameters to compute my particular solutions. And if you plug the two together, so this is your complementary solution, and this is your particular solutions. And this is the formula for exact solution to equation 1. So the exact solution to the equation 1 can be computed formally like this. So I refer to this as variation of constant formula. So this is the origin of the so-called exponential integrators. So you compute your solution based on this exponential form, since you have the metric exponential here. Okay, so here we have the formula for any time t starting from t equals 0. So for our numerical approximations, I'm gonna integrate instead from 0 to t, here from tm to tm plus 1. Okay, so it's actually just like the previous slide, except that now I replace the t equals 0 by tm and the t by tm plus 1. So this is the equations that you have. And this will be the root of my approximations. So I want to derive a numerical solutions u at m plus 1 using this formula. So I assume that I know the solution as um. So the only thing I need to do is how to approximate this integral. So to approximate this integral, I'm going to use the so-called exponential time differencing methods. So the idea of ETD, exponential time differencing method, is that you're going to approximate this nonlinear functions using polynomial interpolations. And then you can integrate exactly the resulted integrand. And so you have some approximations. So ETD or exponential integrators are not new at all. It's actually very, very old. However, when it first introduced, it didn't attract a lot of attention, because of one thing is that computing this metric exponential is very costly. If not, it takes a lot of time, so people don't really pay attention to it. However, in 90s, they have developed new algorithms to compute metric exponential more efficiently based on either Pade approximations or Krylov projection techniques. So that have make the method revived. And so these days, they have also enhanced the algorithms to compute metric exponentials really fast. So that's why we're interested in this, this method. So I just want to give some illustration about the first order and second order ETD method. So for first order, it's very simple. You simply replace your nonlinear to be a constant function at tm or tm plus 1. It's up to you, it doesn't. For this nonlinear problems, and then this matters, so we have to evaluate at tm only. So this method is like explicit, but it actually implicit in some sense, because here you have the metric exponential. I'll come back to that later. For the second order, you use linear interpolation. So here's just constant, and here you have linear interpolation. And so you can compute the integrand after you approximate f by linear interpolation. And here the u tilde is just is obtained by performing ETD1. So you first compute some approximations of u at m plus 1, and then correct that. It's like correcting, two-step correcting. And then you have a second order approximation for u. And in this formula, I highlighted in blue the action of metric exponential and vector. So these are the main troubles of exponential integrators, in the sense that the computations can be costly if you do not do it in a efficient manner. So phi here are called metric exponential functions. It can be divided until phi n. There is a formula for that, but I stop here as phi 2 because I just, yep.
Can I just ask a question? I mean, heuristically, based on what you said, and you can go to higher order,
yes,
expansions, right?
Yes, any order, but there's some requirement on the coefficients. So it's not just any linear interpolations. There's some requirement on the coefficients, so that you can preserve the order of accuracy.
Okay, thank you.
but up to 3 or 4th order is easy. But if you want to go higher, it's more sophisticated.
Thảo Phương, anh hỏi cái này tí.
Yeah.
Cái phương trình của em là steep có nghĩa là cái chuẩn của L phải to, đúng không?
Yeah.
Thì bây giờ anh viết L đó là L1 cộng L2. Cái phần L1 là nhỏ và phần còn lại anh vượt qua bên cái phần non-linear term, thì anh thấy tất cả những cái gì em nói nãy giờ nó vẫn đúng. Có nghĩa là em hiểu anh không?
In fact, I do the other way around. Thường là mình sẽ chuyển từ cái non-linear qua cái linear.
Không, ý nói anh chỉ thấy như vậy thôi. Vì nãy giờ anh không thấy bất kỳ một cái requirement nào trên F hết. Cho nên là khi cái khó em nói, cái khó của em là tại vì L to. Giờ anh tách L đó làm L1 cộng L2, L1 thì nhỏ, L2 thì anh quăng vô trong F. Như vậy thì cái bài toán không còn steep nữa.
Đúng rồi, nhưng mà F khi đó sẽ steep.
Không,
F
ý nói
steep.
nãy giờ anh thấy tất cả những cái phân tích của em từ nãy giờ không có bất kỳ đòi hỏi nào của F cả.
Tại vì em chưa có nói đến F, giống như hồi nãy em đã nói là for simplicity thì em chỉ assume là L nó steep thôi, còn F thì không có steep. Nhưng mà thật ra F steep thì doing this approach nó cũng help a lot. Bởi vì nếu mà F let me see. Nếu mà F steep in the sense that its Jacobian has purely imaginary eigenvalues, là in that case implicit methods won't work either.
Ok.
Yeah.
Có nghĩa là ok, chút nữa em giải thích cho anh tại sao mà nó không work. Bây giờ em tiếp tục.
Okay, yeah. So what I'm talking. Oh, okay. I think I have to speed up. I don't have much time. Okay. So exponential what are the advantages? So like I mentioned, the trick is that since we integrate the stiff part, so this is the main course, at least for this context. So here I assume only stiffness on L. So when you integrate L exactly here, like here, there's no issue with stability if the stiffness coming from L. So large time step size can be used, and because we use sort of very exactly, so we use very exact form of the exact solution. So it's highly accurate and less expensive than solving nonlinear systems. So it's this statement is really for highly nonlinear problems. So for highly nonlinear problem, the cost of the nonlinear solver can be very expensive. In that case, by doing this, it will help. However, like I keep saying, the cost of exponential time integrator really come from the computing of metric exponential. So to overcome this, there are 2 possible approaches, at least for my understanding. So the first way is to improve the efficiency of metric exponential approximations. So there are quite a few works in recent years to improve further numerical approximations for metric exponential. And another way is to use domain decomposition method, because if you can reduce the size of your matrix L, then the calculations will be significantly reduced. So this is the idea here. And if you can perform on the metric exponential locally and in parallel, then that means you save a lot. So you break the bigger one into smaller pieces, and then you do it in parallels. So that is the idea of the method I'm interested in this called localized ETD methods. Okay, so this method actually have been tested numerically on a very large scale problem. So this is the picture from this paper. So in this paper, they do 3D coarsening problems. So basically you have an equations which is Cahilar equations. And here on the left-hand side, you have, so this is an alloy. So an alloy is a metal that is formed by 2 different metals. And this is the coarsening process. So due to heat, high temperature, the 2 metals gonna, be coarsened. So these are the grain. The grain size become bigger and bigger. And what I want to say here is that these simulations have used about 10 million cores. in a very efficient supercomputer, and it is able, the simulation can be done because it's used localized ETD methods. So instead of doing on the whole domain, they do actually locally and perform ETD so that they can do large time step size. And the method is highly scalable. However, mathematical analysis at that time, which is in 2016, is still open. And so we would like to study the sort of mathematical properties of this method. So we consider a very simple problem. So this is a simple but still very trouble because of the exponential matrix. So here, this is the simple linear parabolic equations in one dimension. So here you have the time derivative. This is the diffusion, sort of diffusion, but it's just second order terms. And then you have a nonlinear term, Fu. And we have some boundary condition on the left and right. And there's some conditions on the nonlinear functions. So it is continuously differentiable, and it must have, there's some role such that this inequality is satisfied, and the derivative is bounded from above. So there's certain examples. In particular, I want to point it to the second one. This is S minus SQ, which correspond to the Allen-Carr equations. And here are the upper bound is just 1, since this is 1 minus 3s squared. And for any row, it's not just one row, but any row greater or equal 1, you will have this property. So F row is negative, while F negative row is positive. So that's one model problems that we're looking at. So now, first I'm going to discretize in space. I use very standard discretization. This is finite difference, it's central finite difference. So basically you discretize your interval from 0 to L, and then you approximate the solution at these grid points. So UI is the approximation of U at Xi, because your boundary informations are given. So you actually just have a vector from U1 to UN that are the unknowns. And by using finite differences, you basically obtain the following system of ODEs. So here AN is a matrix from finite differences here, and F is just the action of F at each UI. And B here represent the boundary data. So you have the boundary data at the first and the N points only, G1 and G2. So just look at this system. And now I want to solve this system. First, I'm going to introduce stabilizing constant S. So this stabilizing constant is actually a very well-known technique in the community of Allen-Carr and Kahiller equations. So by introducing this stability, this stabilizer, it sort of help you to reduce the constraint on the time step size. So it's a very useful trick. So basically you're just adding and subtracting SU. So the idea here is really coming from the stiffness of the nonlinear terms. So here you will see this later, but let's stick with this by now. So I have AS instead of A. So AS is just A minus S, and FS is just sum of F plus SU. And now I'm gonna apply my exponential integrators to have the numerical solution in time. So this is the same as before, except now my nonlinear term. So I group these two together because this depending on T and U at the same time. So this is my nonlinear term. And this is the linear term, which is just AS. And so I do metric exponential here. And I can define ETD1 or ETD2 as before. And there is a important result about this semi-linear parabolic equations. For parabolic equations, for linear parabolic equations, you have a maximum principle, and we really need that in our analysis for the convergence of our two subdomain or multi-subdomain solutions. And here for this semi-linear parabolic equations, we have the so-called maximum Bell principle. It says that, okay, so there's some requirement here. So for the stability, for the stabilizer, we require it to satisfy these conditions. So it's sort of reducing the, what to say? So when, so F prime here is like the Jacobian of F, when you have a system. So you don't want the Jacobian is too small in the sense that too large in magnitude, because that will cause issue. So here I'm gonna sort of making it smaller or closer to 0. So that's why I impose S here, greater or equal than this maximum. And for Alenka, this is basically just saying that S greater or equal to. And then with that conditions, I will have the maximum Bell principle. So if my initial conditions and boundary conditions are smaller by rho, this is the same rho that I stated at the beginning for F, then my numerical solutions by ETD will also be bounded by this rho. So this maximum Bell principle is actually true for the continuous case, space discrete case, and fully discrete problems. And I need this for my conversion analysis. So now I go to the overlapping multi-domain problem. So this is the main part of the talk. Okay, so instead of doing the metric exponential on the whole domain, now I try to do it locally. So I'm going to illustrate the algorithm for two subdomain only. And here I'm doing overlapping subdomain. So I decompose my interval 0L into two subinterval 0 beta L and alpha L to L. And now I'm going to solve the problem in each subdomain with Dirichlet conditions. So this is overlapping domain decomposition. So in order to recover the same solutions as if one solved the problem on the whole domain, we need to impose continuous condition here. So the solution at the two interfaces must be the same. So that's why I have here, V is the solution in the first domain. So V must be equal to W at the boundary of the subdomain 1. And W must be the same as V at the boundary of the omega 2. So this is very standard. And now, as in the monodomain case, I'm going to discretize my problems using central differencing, central finite difference formula. And so I obtain very similar system. However, what I want to point it out here is the boundary term. So for subsystem 1, in order to solve the problem, you need boundary data from your neighbor. And for the second system, you need boundary data from the first system. So the two systems couple together. And we can prove the equivalence between these two subsystems and the one that defined on the whole domain, which is du dt in the right-hand side. Okay. And here, I show one way to decouple the system. As you can see here, you cannot solve one system without knowing the solution from your neighbor. So one way is to decouple by iteration. So I assume that, okay, I know my solutions at the k iteration, and then I'm gonna update my solution at k plus 1. So keep doing that. And in that case, we call it Schwartz waveform relaxation iterations. And this is continuous in time. So this is called waveform relaxation. And we can show that this algorithms converges to the solution VW at the linear rate. However, for numerical results, we observe superlinear convergence, not just linear convergence. And now I go to the fully discrete, because this is semi-discrete in space, so time is still continuous. So next I'm going to do fully discrete. So for fully discrete, I will discretize in time using ETD. So I have the solution in each subdomain. And again, I can have first order or second order, or you can have higher order. I stop at second order here. So this is an example of the first order one. So, so it works as follows. So to compute the solution in the first subdomain, you're going to perform metric exponential, and you're gonna compute the boundary at m+1, and this information is given by your neighbor. Okay, so the B term here depends on your neighbor, the boundary data, and same thing for B2. And there's one thing I would like to mention, that differently from the space discrete system, the multi-domain here, the discrete multi-domain solution, it is not equivalent to the mono-domain scheme. So if you do mono, that means this is how you do it on the whole domain, and you do metric exponential for the big matrix. These two systems will give different solutions. They are not the same solution. However, when delta t go to 0, the two both converge to the semi in time. Okay, so it's discrete, space discrete. So they both converge to the exact solutions that is continuous in time. So that is the key difference, because this is not the case when you do implicit time stepping. For implicit time stepping, you will have equivalence between the multi-domain solution and the mono-domain solution at discrete level. However, here this is not the case. As in the continuous case, here I'm going to decouple these two systems because they are coupled together by doing iteration. So there's two ways to do it. Either you do iterations at each time step. So that means, okay, assume that I know the solution at Tm. So Vm, Wm are known. And I need to compute V and W at Tm+1. Okay, so to do that, I'm gonna impose some initial guess on the interface. This is the value on the interface, and I do iteration only at the time m+1. So I iterate until it converge. So that is one step iterations. So at each time step, you do iterations. When it's converged, you move to the next time step. So that's one step. Case. For the second approach, you're going to do it globally in time. So you're not doing at each time step, but now you assume that you don't know the whole interface from time t equal to 0 until the capital T. So you're gonna set initial conditions, initial guess for your interfaces to be along the time interval. So it's going from m equals 0 until m equal capital M. And then you're going to do iteration over the whole time interval. So it is why we're interested in this case, because it's reduced the communication time, since you exchange all information in space and in time at each iteration, instead of you do at each time and you exchange. So that's communication. And also by doing global in time, one can use different time steps. Okay. So now,
Phương anh hỏi cái này tí.
Yeah.
Cái initial guess có dễ kiếm không?
If we have initial conditions, we just use the initial condition.
Okay.
Yeah. So now the conversion analysis. So there's two results. So first, I show the conversion of the iterative solution. So this is the iterative solutions. You start some initial guess and you do iterate until you converge. So this is the first conversion analysis. So one can show that the iterative algorithms will give you the solution when k go to infinity for both methods. And your discrete solution also satisfy maximum bound principles, the multi-domain case. And the second convergence result is that, as I mentioned, the fully discrete multi-domain solution is not equivalent to the mono one. So here I show that the localized ETD solutions converge to the exact space discrete solution as the correct order. So it's first order or second order depending on ETD1 or ETD2. Since I don't have much time, I really have to speed up. So here I show you numerical examples that illustrate first the accuracy of the method and then the convergent behavior. So on the parameters here are very standard. So I will switch to the results. So first I'm gonna verify the accuracy in time by looking at some non-zero solutions. So I started with some initial and boundary data and I compute the reference solutions by running the scheme on a verified time step, and then I compare with my approximate solution. So here I show that the rate, if it's first order, so the rate is 1. The rate of convergence here, for those who not, especially students, meaning that when you reduce the time step size, for instance, by a factor 2, your error also reduced by a factor 2. So that's first order convergence. If you have second order convergence, that means when you reduce your time step size by a factor 2, your error reduced by a factor 4. That is 2 squared. So that is second order convergence. And here we observe first order and second order convergence for any overlap size. So this is the size of our overlap. I will talk about the effect of overlap now. So next, I'm gonna sort of analyze the convergence behavior. So for that purpose, I'm gonna looking at the error equations. So it's like you're looking at the difference between your approximate solution and the exact solution. So you end up with an error equations. So it's like you have exact solution just is 0. And then you start with some initial guess, and then you see how the errors are reduced at each iteration, because theoretically your error will go to 0 when k go to infinity. So the more iterations you do, the smaller the errors it will be. So here's the effect of convergence with respect to overlap size. So I increased the overlap size from 2, 4, 8, 16, and 32. So this is a very classical result of overlapping domain decompositions, meaning that the bigger the overlap size, the faster the convergence. And both observed for method 1 and method 2. Method 1 means you do iteration at each time step, and method 2 means you do iteration over the whole time interval. And there's a more interesting behaviors, meaning the convergence with respect to the time step size. So for the first method, we expect that the smaller the time step, the faster the convergence will be, since no updates, right? If you have very small time steps, then you actually don't update a lot. So that's why convergence very fast. And this is the case. However, for the global in-time methods, since you do it globally, so the iterations does not really depend on the time step size. So it's quite independent of the time step size. And this is another feature, nice feature of a global in-time approach, saying that you don't depend on the time step size. However, it does depend on the final time. So the bigger the final time, the slower the convergence, which is very reasonable since you have more information to exchange. So you require more iterations. So that's basically it. And then I have the 2D example, even though the analysis is just for 1D, but it actually works for any dimensions, just like the 3D case I showed at the beginning. So here, the purpose of this slide is to show that for any method, method 1 or method 2 with different decomposition. So here you have 2 by 2, 3 by 3, 4 by 4 subdomains. This means you cut it in 4 in each directions. Then both methods will give you the same accuracy as you do globally. Globally mean on the whole domain. However, method 1, the number in the brackets are the number of iterations, require very few number of iterations. And this is the ideal number because here you have 2 by 2. So it is it is designed that you have the same number of iterations as the number of supplement per directions. So method 1 in this case is really sort of outperform method 2, because for method 2, if you stop at 2, the accuracy is not reached. You have to go 12 iterations or even more to obtain the desired accuracy. However, to give a fair comparison between the two methods, is really need to take into account the computational cost and the communication times, and the test case also need to be well designed. So for this test case, method 1 is outperform only. Okay, so I have 5 minutes to finish this. I already ran out of time. I will do it very quickly. So in this case, I consider the so-called shallow water equations. So shallow water equations are equations used to model surface flow, free surface flow, but thin layer, like what you have near the coast. So you're interested in the horizontal scale instead of the vertical scale. So it is spreading horizontally and thin layer. So shallow water equations can be seen as sort of a depth average of Navier-Stokes or Euler equations, depending on you consider viscous or inviscous fluid. So here we have the conservations of mass and conservation of momentum. Here I don't go into detail, but instead I just want to say that after spatial discretization of this system, I don't have time to spend that, you obtain the following ODE. So this is an autonomous ODE with a vector unknown to be W. W will be your unknowns depending on what kind of spatial discretizations you use. However, this is a vector, and on the right-hand side, you don't have T appear explicitly. So this is an autonomous system. And we can also use ETD to solve this nonlinear system. So F is nonlinear, and by doing the linearizations. So we rewrite the system in the following. So Jn here is the Jacobian matrix of Fw evaluated at some reference time. So it can be at Tn, your current time, or at some Tn, depending on how you define your reference time. And Wn is just the approximations at Tn, and Rn here is just the remainder. So that this is actually equivalent to this system. And now you have the linear term and the nonlinear remainder, so I can apply ETD, right? And this method is called ETD Rosenprock. Rosenprock basically means you do linearizations and then you apply ETD. So that's called ETD Rosenprock method. And I also developed the overlapping localized ETD method for this problem. So basically you are having a very similar situations. So you have your neighbor, you have interface, and you're going to impose boundary conditions given the information from your neighbor, and you do iterations. So basically that's it. I want to show the numerical result because before I end. So this is the numerical result for Rossby waves. So what are Rossby waves? So Rossby waves occur in the rotating fluid since our Earth is rotating. So this is rotating shallow water equations where you have the effect of nonlinear Coriolis force. And Rossby wave is known for its characteristic that it is very slow motion, and it stretch horizontally instead of vertically. So it is very suitable to use shallow water equations to model Rossby waves. And the test case we consider here is the so-called zonal wave number 4. So you see here the pattern of the wave number 4. And we do it for two types of resolution, 60 and 30 kilometer. And what we're interested here is that for ocean community, they mainly use explicit like Roncutta or semi-implicit method, and we would like to show the efficiency of using ETD compared to RK, and then the efficiency of using localized ETD compared to ETD. So here, this is the accuracy if you use ETD. And here for this model, we use third order ETD to obtain better stability. Yeah, since I run it, we need to run it for a long time. So here we observe third order accuracy. And here I want to compare the computational cost. So in green, in purple first. So purple is the computation. So this is the error versus CPU time. And the purple one is RK3, so third order Runketer. And green one is third order ETD. This is for the 60 kilometer resolution. And you see that the computational cost for ETD is smaller, even though here we have the error is sort of in between and we have the computational cost is smaller. So we can say that ETD and RK roughly give you same computational cost. However, if we do localize, we can improve the computational cost of ETD. So here, this is the time when we have 1, 2, for 1 means you like doing ETD, and when you have 32 processors. So in this case, not processors, it is subdomains because we do it sequentially. However, what I want to say here is that, okay, so now look at the first slide. The total time is 1,400 something second. And the last slide is 2,300. And this last slide is obtained by a sequential code, okay? Even though we have 32 subdomains, we obtain this number. So if we do it in parallels, this number must be divided by 32. Why this is roughly not even double. So that means when you divide by 32, you obtain a significant speed up compared to doing on a whole domain. And for this geophysics flow, conservation of mass and energy is very important. So I show here the conservation of mass and energy with localized ETD. We have more test cases and numerical results in our paper. If you're interested, you may look at that. Otherwise, I conclude. Okay, I'm done. So for conclusion, so I have presented the so-called overlapping spatial domain decompositions. So here we do domain decomposition in space, not in time, combined with exponential integrator in time for two types of equations, the semilinear parabolic equations and the nonlinear hyperbolic equations. So for the semilinear case, we prove convergence analysis, especially the convergence to the exact space discrete solutions using maximum Bell principle. And for the shallow water ones, we see that numerical results show great potential of localized ETD in terms of parallel computing. With that, I end here. Thank you, everyone, for your attention.
Thank you, Thảo Phương, for a very nice talk. So now it's open for question. Maybe anyone have question for Thảo Phương, you can ask now. We can start maybe students. If you have questions, you can go ahead. Student or grad student.
I have one question. When did you compute the error? Did you compute the error of the transform solutions with a transform exact solution, or